What we're going to talk about today is gases. You'll see right up on the top of this chart, we have to start with talking here a little bit. You see this word cryogenics, and probably a lot of you have never heard that word before. Cryogenics just simply means, it comes from the Greek word. When we talk about the states of matter, we're talking about these liquids that are boiling. And the states of matter, there's only 3 different states of matter. Who can tell me what those are? Yes, sir.
Solid, liquid, and gas.
You got it. Solids, liquids, and gas. Because it goes from a solid to a vapor, just like this is doing right now. That's called sublimation. So when solids go directly to a vapor, it's called sublimation. When they go directly from a vapor to a solid, what's it called? It's frost. You see frost in the morning, you see the moisture on the grass. It's a solid frost that's out there. Now in this cylinder, we have liquid carbon dioxide because the pressure in here is above 80 pounds per square inch. It's 800 pounds per square inch, or a little more in here. And if you take this liquid, this is a CO2 fire extinguisher. If you take this liquid CO2 that's in here, carbon dioxide, and release it, take the liquid right out and release it to the atmosphere, you get carbon dioxide solid snow. As a matter of fact, the machine we have that makes these pellets is simply we take liquid carbon dioxide from a big bulk tank that we have, and we blow it like this. We blow it like that into a chamber, and then a big piston pushes all that, and it's a big snowball making machine, really. It takes that solid snow of CO2, of carbon dioxide, and blows it, pushes it through some holes in a big plate, and makes these little 1/2-inch diameter pellets, which are easier to handle and they're more dense, and you get more solid carbon dioxide to play with that way. So that's kind of what's going on there. So there's 3 different states of matter: solids, liquids, and gases. You can take the solids and melt them like ice would do. You can take the solids, and some of the solids go, and that's called melting, and you can take the solids like carbon dioxide, dry ice, and it goes directly to a vapor. That's called sublimation. You can then go from the liquid to the solid, and you can go like a liquid to a solid is freezing in the case of water, freezing into ice, and of course the water then melts. Or you can take it and evaporate the water, or you can condense it. So those are the only things that can happen to the states of matter is those 6 different things. We're going to take one of these just to show you what's going on with these pieces of dry ice. I'll put some in this little beaker, and you can see that it's just sitting in there. It doesn't look like it's doing anything, but in fact it's gassing off, it's subliming off, and you can see that it turns into a gas. And I need to put more in there. So it'll work a little better. So as this just warms up, it'll turn to a gas, and you can see that eventually it'll fill that balloon up. I'm not going to stand here until it does, but you can see that that solid carbon dioxide is just subliming off into a gas, and it's building up a pressure to fill up that balloon. Now, if we took liquid nitrogen, which really does not want to be, these gases do not want to be liquid. As you can see, here we have it in a vacuum-insulated container, and it's sitting there boiling away just from the heat that's leaking through that vacuum-insulated container. If we take that liquid nitrogen, let's pour some out here. Now it's going to take a little while to get this. This measuring cup is a Pyrex thick, heavy thing, and it takes a lot of nitrogen to cool it down to 300 below zero. So this Pyrex measuring cup is being cooled to 300 below zero right now. Of course, to do that, it has to remove the heat from or add the heat to this liquid to boil it off. And if we take some of that and pour it into this beaker, cool down. And now we put this little balloon on top. You can see that that's really boiling off really rapidly, and it'll fill that balloon really fast. It's just going from the liquid to the vapor, or to the gaseous nitrogen. That liquid, a cubic foot, or a gallon, whatever you like, a cubic foot of liquid nitrogen will expand to 700 cubic feet of nitrogen at atmospheric pressure. As we see it now, and oxygen's 860 to 1 ratio of when you boil a liquid off into a vapor. We're going to, some things you can do with, when you have these liquids expanding like that. I heard a story of a guy that down in Texas who had a golf cart, and his golf cart was powered with liquid nitrogen. And the way he powered it with liquid nitrogen was he just simply used the pressure from the tank to drive a little engine, which is what this is. This is a little steam engine that was made in Germany, and it's got a little piston and a little wheel that goes, and it's designed to be used with water. Of course, it's designed to have a fire underneath here. You put water in it, and then you build up the pressure, and the pressure pushes and makes this thing run. But we're going to do that with liquid nitrogen. So I'm going to take this liquid nitrogen. It's a little tricky to do. I'm going to pour this liquid nitrogen into the engine, and then rapidly try to plug it up with this plug and not get myself too cold. And then you can see the little wheel going. I always wanted one of those when I was a kid, and so I finally got on eBay and found one of those things. And you can see that by letting the nitrogen build the pressure up in there, it did the same thing you would do with steam. You build the pressure up, and you are able to drive a... And so this guy had a big liquid cylinder full of nitrogen on his golf cart, and he had an engine similar to that little engine there, a lot bigger obviously, and he was able to power his golf cart with that. Another thing just to show you a little bit about how the pressure, we need a little more nitrogen, builds up and what it does to some of the materials. There's a lot of research being done and has been done over the years to develop materials that will withstand the temperatures of outer space. We talked about the blue sky, but what color, when you're up in a satellite or up in the research station up there, what is the color of the sky that those guys see, the astronauts when they're walking around? What color is that? Black, really black. There's no color there to it at all. And but while they're up, before they got up there, somebody had to do a lot of research to develop ways to materials that they could use that would work good. And for example, here's a rubber hose. We're going to take this rubber hose and let's just see what happens to it when you cool a hose down. Do you think this rubber hose would be a good material to use up in a research station or on a satellite of some sort? Now watch what happens here. If we put this down in there and we seal this off, it builds up the pressure in there and allows the liquid nitrogen then to escape through the hose. And as you can see, that probably wouldn't be a good thing to use up in the space station. It freezes it solid, and it'd be like brittle, like glass. I could break a piece off, but I want to use that again sometime. I can use it next time it does on me. Another thing relative to some of the pressures is that when you heat a gas, it expands. When you cool the gas, it shrinks. And I want to just show you a little bit about how much these gases shrink. I'm going to get some more of it here.
That would just melt your skin.
What's that?
Freeze it, but be some cold and burn.
Yeah, let me just see if I... What I want to do is this gauge here, it's full of glycerin, but this is a pressure gauge. It's a vacuum gauge. And what I'm going to do is, watch what happens when you, now this little glass here is filled with, this flask is filled with air, obviously, it's exposed to air. I'm going to put this gauge on it, which is a vacuum gauge, and it'll show you what happens if you cool the air down. Now, you're not going to read the numbers too well. It'll read down to minus 30 inches of mercury. It won't go that far. But if I put this in this liquid nitrogen, you'll see that it's going to shrink the air that's in there and cause it to pull a vacuum. And this is a way, there it goes. This is a way, one of the ways where people pull vacuums, and they use liquid nitrogen to sometimes in conjunction with some adsorbents, to actually drop the pressure by just cooling it. And you can see the pressure is now down to minus 10, and it's going down pretty fast. It would eventually go all the way down to where it liquefies the oxygen in this container, and it would get down to a pretty low pressure. You can see that there it's 15. It would keep on going, but you get the point. But now we get to have the real fun. We're going to take, we're going to need some more nitrogen. We're going to take a balloon, which we kind of hold down here. We're going to take the balloon, just hold it down a bit. We're going to pour liquid nitrogen over it. Let's just see what happens to that balloon. We shouldn't have filled it that full. So we're going to pour liquid nitrogen all over this balloon. So here we are cooling this balloon down to 300 below zero. Let's just see what happens to it. So what else is in here? This was just filled with somebody's air that they blew in there, which has CO2 and oxygen, and it's not just nitrogen in this balloon. And this will just shrink all the way down to where it's completely flat. And if you look real carefully in there, you'll be able to see some liquid floating around. You probably can't see it out there, but there is liquid floating around. That's liquid oxygen floating around inside there. Because what's the boiling point, again, of liquid oxygen? The boiling point of liquid oxygen is minus 297. The nitrogen is minus 320. So the nitrogen is cold enough to condense the oxygen right inside that balloon, which is what you just saw. And right back to where it was. Oh, there's still a little bit of liquid floating around in there. Liquid oxygen. That's kind of cool. So I'm going to take this balloon.
There's probably some water in there too, right?
There might be some water in there. There's a little bit of frost, it looks like, in there. And so we'll, I think we need some more. Wait a minute, we need some more nitrogen. We'll do that again. Let's just see what happens with this one. pour the liquid nitrogen over this balloon. Here we go again. Now when you see this vapor all flowing around here, what do you think that is? Is that nitrogen that we're looking at? Nitrogen, as you can see, is colorless. It doesn't have any color at all. So what's all this vapor we see flowing all over the table and everything like that? It's really just moisture from the air that's gotten so cold that it just condenses out and dews out and makes a fog. And that's water. And you'll see that this won't go down as far as the other balloon did. Now let's just let it sit there and see what happens to it. It just fills right back up just like the other one did. Only thing is with this one, it's just going to go up. Stop! It just stopped right there when it goes through. Of course there's a string here. Most of you can see the string. And not all of you can. But if when I'm on a big stage and it's got a black background, I use a black thread. I saw that this was white, so I used the white one. And quite often nobody can see that thread. And they think I'm really magical by stopping that thing in midair. So anyway, so why did that not go all the way down as far as the other one did? Because in the other one we were really literally liquefying or totally condensing all the way down. The helium boils at minus 452, and the nitrogen just isn't cold enough to liquefy the helium, obviously. So, but it does shrink it, as I mentioned. When you heat gases, they expand. When you cool them, they shrink. And you just saw the helium shrink down to pretty small size, but not all the way down to where it becomes a liquid. Helium is the only substance that will not, that has no solid phase. There is no solid helium that's ever been discovered. And there's been research done where they've been able to get almost down to absolute zero, minus 459.7 degrees Fahrenheit. That's the coldest you can get. All molecular motion stops at that temperature. And they've been able to come within fractions of a degree Fahrenheit of that temperature in the past, in certain research places. If you take liquid nitrogen, somebody's going to ask, what happens if you put your finger in there? What happens if you put your finger in there? First of all, if you get, within 30 seconds, you're going to have a third-degree burn. And shortly after that, you're going to, your finger would be solid, and you could hit it on a table, and it would shatter like glass. One of the uses of liquid nitrogen, which probably surprises you if you were going to just do a little bit of a thing here. It's used in a lot of manufacturing operations where for example, if you wanted to make perfume, a lot of the perfumes come from flowers. I mean, they get the fragrance from flowers. And so to process a lot of flowers, you need to get a lot of flowers, and you need to handle them. And rather than sit there and pick these off one by one, which would be a pretty expensive thing to do, they literally cool them in liquid nitrogen. Let's just do that and see what happens. Cool that flower down. It's too bad it's kind of a nice, pretty flower. It matches my coat. These were donated this morning by Flower Country Downtown. What they do then with these frozen flowers is they just do that to it. And then they can handle it. It's all frozen in solid form, and they can ship it, handle it, process it, and do things with it that makes it a lot easier. I'm going to do one other thing here, because we talked before about that rubber hose. By the way, that rubber hose now is back to being what it was before, and it's useful for what it's intended for. But I'm going to, let's just see what happens to a rubber ball if we freeze the rubber ball. This is not the greatest place to do this. Maybe we'll do it anyway.
Under that wall.
Yeah, we tried the wall. There we go. Let's just see what happens if we freeze this ball. Let's put this down in here. How much time? We have up until 2 o'clock or something, did somebody say? All right. We're going to do the whole show. So what we'll do here is, what did I do? I've been doing all this stuff. This is one place where you really need it. My glasses would do a good job of keeping this away. I haven't been splashing this stuff around much, so. So we'll cool this rubber ball down, and let's just see what happens to that. It did previously. I mean, this is I know it's a handball ball or something like that, but I mean, it is a rubber ball that bounces and does what rubber balls do. And let's just make sure we got it good and cold. Make a little room here. Lock this off. Let's see what happens with that. Don't touch that. That's 300 below zero. That'll burn you a little bit if you touch it. It'll warm up pretty quick. So that's what happens to rubber when it gets cold. Now we're going to take a little piece of we're going to take something else and cool it down. A little more room. Let's just see what happens. I've got a couple pieces of wood here, and I've got a nail, and we've got a little piece of rubber like this that's just a little shaped in a sharp piece like that. And what I'm going to do is take that little piece of rubber, and let's see what happens to that when we cool it down. We're also going to take a banana. And let's cool a banana down. Now that'll take a little while to really get good and cold. How many of you here, is anybody here, how many of you have never had a McDonald's hamburger? Usually there's somebody in the audience when I do this. In fact, I just did one Tuesday in Hornell, and there was like 6 or 8 people never had a McDonald's hamburger. But all McDonald's hamburgers have been frozen with liquid nitrogen. Now, why would anybody freeze a hamburger with liquid nitrogen? Because it really preserves it, it freezes it really quickly. It holds all the nutrients into it. It holds all, yes?
It doesn't give off water when it's evaporated, so it doesn't spoil the meat.
Right. And it keeps the quality of the meat really, really good. I mean, they could use blast freezers or some other ways to freeze the meat, but they've elected a long, long time ago. It was back around 1970, I think they started freezing their hamburgers with liquid nitrogen, and they ship it all over the world. There's a plant in Chicago back then that would get 5 carloads a day of cattle in one end of the plant, and they would get, I think, about 4 18-wheeler loads of liquid nitrogen. They would chop up the cows and make hamburgers and patties and freeze them all with liquid nitrogen. Let's just see what happens when you get a banana really, really cold. let's see what we can do with it. For one thing, we can probably drive this nail right down through there. I don't think the woodworking classes do it this way, but at any rate, that is one way to stick things together there. And another thing we can do here is let's just see what it does to this little piece of stuff here. This little piece of rubber that was a piece of rubber before. And now it's curved, which isn't the greatest. So we will drive that piece of rubber right into the wood also, and it's very, very solid, not bending at all. So these are some things that that liquid nitrogen is used for. They're very practical and they work good, and it's done every day. Also, let's talk a little bit again about some of the materials. One of the things that some of you, some of the welders, Dresser-Rand, and some of the welders are over at Dresser-Rand, I understand. Dresser-Rand shrink fits wheels onto the shaft of their compressors. And the way they do it is they heat the impeller, which expands the metal. It slides over, it's all carefully machined, and then when it cools, it shrinks right onto the shaft, and it's really locked on really, really tight. It's very difficult to get them off. They have to use big torches and things like that to get them off. So what I've done here is just to show how metals shrink, is I've got this ball bearing, and we've machined this aluminum plate so that the ball just barely goes through it. Now what I'm going to do is I'm going to take this aluminum plate, cool it down to liquid nitrogen temperatures, and then see what happens to it. There you go. It's still cooling down. I guess that aluminum takes a little harder to do that. Cool down and the other thing. So let's just see what happens now if we try to put the little ball bearing through it. You'll see it won't go through because the aluminum has shrunk all around that ball bearing and it won't go through there. Now, I'm going to let that sit here, and eventually that'll warm back up again, and it'll scare the daylights out of me when that thing drops into that cup in a few minutes. I wish I had a long, narrow pan, but I guess the only way to do that is to pour this in here. We'll use that big tray. So let's just talk about some of the other materials, that they have to try to figure out what materials to use out in outer space. And I've got two different rods of metal here. One of them, let's just take this stainless one. Again, that's stainless steel. Let's just bend it and see what it does. It bends pretty nice. Let's just cool that down to liquid nitrogen temperatures if we get some more nitrogen. And we'll see what happens to the stainless steel once it gets cooled down to liquid nitrogen temperature. Now let's take this steel rod, again this is steel again, and let's put it in here and bend it and see what happens to it. Yeah, about the same, bends pretty easy. So let's put these in liquid nitrogen, put this in liquid nitrogen also and see what happens to it. Physical properties change of almost everything when you cool them down and when you cool them down to these really, really low temperatures. For example, this stainless, which is now been cooled down to 320 below zero, let's try to bend that. Then it's just as easy as it did before, no problem. Well, stainless steel will probably work pretty good out in outer space, but and I'm sure a lot of things are made out of stainless steel out there. Let's just see what happens to, oh, it scares me every time. So this thing finally expanded out till it, the little ball fell through, and I jumped. And now let's see what happens to the steel when we cool it down to 300 below zero. You can see the steel gets like glass when you cool it down like that. As a matter of fact, if you cool steel down below 20 below zero, up in Alaska where it gets 30, 40 below, 50 below, 60 below, Alaska 80 below, you can have, I mean, construction machinery, all that kind of thing that has to be taken into consideration. You have to build things out of steels that are going to be able to handle those cold temperatures.